Yeah, welcome to another presentation. This is lecture number 42. In this presentation, I would like to explain about the analogous system. Analogous, something I think I somehow I missed. I think during in our this becomes during this block diagram, whereas first it belongs to the first unit of course topic. Here this is also one of the very important topic basically we need to consider. Just as I recall my presentations, I have noticed that this particular very important topic is missed. That's why I want to give you the explanation, and I want to do one more presentation on this topic, analogous system. Okay, so what is analogous system? Analogous is nothing but equivalence. Equivalent, otherwise it is called equivalent. So what equivalent actually, what is the equivalent, or for which means that if you recall your first mechanical, I think we have discussed somehow, we have done some examples also on mechanical translational system as well as mechanical rotational systems. We have discussed in our previous presentation, if you recall. There we have seen actually, so how the mechanical translation systems represented and how the rotational systems are represented. Clear? So then for those two types of systems, we have seen, we have derived the transfer functions. Just I think we have missed the analogy part. Analogy means to convert this given mechanical system into corresponding equivalent electrical network. Okay, so the mechanical system will be given, either it could be because however, so under mechanical system it will comes basically, I will brief you. Under this mechanical system, basically we have two types, two categories. That is, one is mechanical translational, mechanical translational, mechanical translational system, and second is, it is mechanical rotational, mechanical rotational system, rotational system. So it is a mechanical translational. Translational is nothing but you can it can be shifted from one place to other place. You can, okay, you can shift that. You can shift this. You can maybe from one place to another place you can shift, or you can place like that. So that is what mechanical translational means. Okay, whereas mechanical rotational means, in this particular system the major important thing is it rotates basically like armature. If you see the motor, AC motor, generators, or whatever it is, some electrical, so the rotating part, no, it will rotate the armature like that. So that is what the mechanical rotational system means. It is not that one actually. So this is something, blocks will be given mechanical system, you can shift from one place to other place like that. So in mechanical system, basically we have seen the examples how, I mean, what is the transfer function, how the transfer function will be find out. For both we have covered actually in transfer function point of view. But whereas, say for example, for any given physical system, I mean for any given this particular mechanical translational system, the corresponding equivalence of electrical circuit we have to convert into equivalent electrical circuit actually. Okay, say for example in this mechanical translational, the main elements what we have are basically mass element, nothing but your m, denoted by m. Next is the dash pot coefficient. I think you have remembered this, dash dash pot, or otherwise also this is called as damper. or friction coefficient, whatever it is, that is represented by letter B. And then spring coefficient, spring actually, spring, that is denoted by the letter K. And then the force, obviously the force, applied force actually, that is F of t, applied force is the F of t. And another is the displacement. Okay, so the displacement here is x. These are the various elements, various parameters associated with this mechanical translational system. This is displacement. And then if you take the x dot, that is nothing but first derivative dx by r, your x equal to normally q here. Okay, your x is normally or otherwise I will explain you later. Displacement x. And then the velocity, second is the velocity. Velocity is nothing but x dot, means first derivative dx by dt, these are the different things actually in mechanical translational. Similarly, in mechanical rotational, you will have again like that similar kind of things only, as we have seen here. Mass element, here it's here the moment of inertia, we will consider the moment of inertia in this as the required parameter. Mass element, that is the element is moment of inertia j, and remaining all are the same. I mean dash pot, again dash pot, it is capital B. And then spring, you will have as it is in this also, spring constant, it is k. And then you will have here, this is actual displacement, normal displacement, whereas in rotational you will have angular displacement. This is called angular displacement, theta, angular displacement is the theta. And angular velocity next, angular velocity. So angular velocity is nothing but that is represented by omega, basically here it is d theta by dt. If you take the first derivative of theta, that is what angular velocity. Okay, so and these are the basic things normally. However, the applied force is there again, means here in mechanical translational, the applied here the force will be applied, basically the force is the input element, whereas in mechanical translational the torque is the input element, torque, the torque is input element. Okay, so here the input f of t is your input, whereas x, displacement x, is the output normally. F of t is the input in this case, x of t, your displacement, is the output for mechanical translational. Whereas mechanical rotational system, the input is torque t, and then the output is angular displacement theta, That's why in this case, if you recall our previous presentations, you can easily identify that the transfer function in general, the transfer function for this mechanical translation system is nothing but Tf is equal to, for this system, Tf is nothing but your, what is output? X, normally x of s by f of s. This is what the transfer function for this mechanical translational, because you will consider x of t nothing but displacement. If you take the Laplace transformation of your x of t displacement, that is x of s, and input is f of t force. If you apply Laplace transformation to the f of t, then it is f of s. Therefore, this is what the transfer function normally we have to obtain for this case. Similarly, if you consider this particular mechanical rotational system, there theta is the output, whereas torque is the input. Therefore, by applying the Laplace transformation, theta of s by t of s, nothing, that is what the transfer function. Clear? Now these are what okay, this is the simple classification under mechanical system. So this is the mechanical translation one part, mechanical rotational is the another part. Now these particular systems, either mechanical translational or mechanical rotational, these two can be easily converted into equivalent electrical circuit. That is what the analogy means. That is very important, very simple. in fact. Clear? So these two, either this will be given or this will be given, and they will ask you, draw the equivalent electrical circuit for the given mechanical system. What we need to do? The basic thing is, the very important thing is that you must remember is that, so these are the basic elements involved in mechanical translational systems. These are the various elements. Just we need to know that what is the corresponding equivalent electrical element for these particular mechanical element. These are the mechanical elements actually. So for mass element M, what is the equivalent electrical element? For mechanical element dash part B, what is the corresponding electrical element? Similarly, what is the for this mechanical element K, what is the equivalent electrical element? Likewise, we have to, if you know that equivalent value, then it is obviously your job is over. Clear? Now, let us consider for this mechanical translational. I will explain you this later on. If time permits, I will explain this, or otherwise for this, I will explain you in the another immediate presentation. I will cover that also. Don't worry, and please follow it, and you will enjoy this. Actually, it is a very beautiful presentation and topic. In fact, now let us consider the mechanical translational system. So, mechanical translational system. I can write in simple as system instead of writing total. So here, so what are the elements? Basically mass element M, and your friction element B, your spring constant K, and your force obviously F is there, F of t otherwise, and similarly your displacement X, and X dot is the angular velocity, dx by dt. Actually X dot is nothing but first derivative, you can write dx by dt, that is nothing but velocity basically. Clear? These are what the basic things normally. So again this particular corresponding to this particular for mechanical translation system, your input is what actually? For this, your input is what? F of t, applied force is the input, and output is the your displacement, x of t. Displacement is the output, and your f of t is the input basically. This is input, this is your output. Clear? Now the thing, very important thing to remember is that, say for example, if I am I wish to transfer, or I wish to draw the equivalent of these two electrical, that electrical also should have some input output, is it not? At least input. What could be the input? I have to mention there. So in general, we know that for any electrical circuit, normally the input is obviously either voltage source or current source. Clear? So for the electrical circuit, in general, you take any electrical circuit or most of the electrical circuits, the input is always either voltage source or current source. Means that this particular system can be converted into two ways actually, that is with voltage source or otherwise with current source also, either V of t or I of t. You can convert the mechanical block diagram, mechanical system can be converted into equivalent with some electrical circuit with the input voltage source. Similarly, the same mechanical system can be converted into equivalent electrical circuit with the input of I of t. For this, if we want we want the electrical circuit with input voltage source as voltage, then that is called force to voltage analogy. Force voltage analogy, that is called force voltage analogy. Again here two analogies are there. One is force voltage, okay, one is the force voltage analogy. In this case, your input is f of t, and here in electrical circuit, you will draw the corresponding electrical, no? In this electrical circuit, your input is V of t, voltage. Means that your f of t will be converted to the V of t, voltage source, and thereby correspondingly all this mechanical also will converted into equivalent electrical. So in your force voltage, okay, f of t I have mentioned, no, already f of t it is there. So remember that your M is converted to, your mass element is converted to L, inductance, in force voltage analogy, and your B is converted to resistance R. The mechanical element B is equivalent to resistor of electrical, and K is equal to, it is 1 by C. F of t, obviously it is V of t, just now I have explained that. X is nothing but charge Q, x equal to Q, whereas x equal to Q, then dx by dt is nothing but, dx by dt nothing but, if you place that x equal to Q value here, it is dq by dt. Your dq by dt is nothing but further I, current, or otherwise, okay, dq by dt is nothing but I. Clear? And sometimes you may have d square x by dt square also. This is nothing but d by dx of dx by dt. Nothing but, what is dx by dt? It is I. You can write di by dt. This further you can write di by dt. Clear? So d square x by dt square is equal to, you can write this d by dx of dx by dt. So dx by dt is equivalent to I also, therefore I can write di by dt. Here you can write I, therefore di by dt equivalent. So these are things you must note down actually. And how these will be, how these are equivalent, that I will explain you later, don't worry. So for the time being, just to remember that the mass element, mechanical mass, is equivalent to electrical inductance, electrical parameter inductance, mechanical element B equivalent to your electrical parameter resistor, and then your mechanical element K is equivalent to electrical element 1 by C, and the mechanical force equivalent to electrical voltage source, and your X equivalent to charge. This is charge, basically QH charge. Likewise, we have to convert and we have to represent in the circuit form. Then your problem will be over. So shall we do an example? If we do an example, then you will better understand actually. Okay, then I will explain you one simple example there, how thereby you can understand it very well actually. Very well. It's a very interesting actually. I will explain you. Let us consider a simple example of mechanical system. Just this. This is this is very simple example, very simple example, and a very interesting example even. So draw the electrical, first of all, okay, draw the electrical equivalent, draw the electrical equivalent circuit for the given mechanical system, for the given mechanical system. So for the given mechanical system, so the problem is like this, your problem is given like this. So let us follow this, you will definitely enjoy this. This is some reference basically, Always reference will be denoted in this fashion only. Clear? Now there is a element is given, mass element is given here. This is nothing but your M, and it is connected with some spring constant K. Clear? And then here the friction coefficient is represented by, denoted by B here. Sometimes they will give like this, or sometimes they may show with some circles here. Don't worry. Means there is a friction between this bottom of this block and to this earth. Some friction will be there. To represent that, to differentiate, to indicate that, they will give like this. Nothing. Okay, there is nothing to confuse. Anyhow, B is the friction coefficient, and on this block we are applying F of T is the force, applied force actually, and then here this X is the displacement. X is the displacement. Okay, so draw the electrical equivalent circuit. Okay, in force voltage analogy. In force voltage analogy, at that point, force voltage analogy, we will see the force voltage analogy. After that, we will see the force current analogy of it. Okay, now, so this is the mechanical system. Actually, it is a translational system. It is not the rotational system. So I am erasing this. So here, for any given mechanical system, the first thing what we should do is solution. I am writing actually. For any given mechanical system, if it is given like that, so as we have only one block in this particular problem, you have only one block with one displacement. Therefore, you have one differential equation. Definitely, you will have only one differential equation. If two blocks are given, definitely there should be two displacements. If two blocks are there, then you will have two differential equations. So the number of blocks indicates the number of differential equations. Remember that. The number of blocks indicates the number of differential equations. So in this particular, we have only one block, that is M. Therefore, we have one X. So first of all, what we should do, you write the differential equation. You write the differential equation for this. So what is the differential equation? It is nothing but, otherwise it is not required to represent all the free body diagram, because I already explained in the previous slide. Okay, that's you already well known. So by knowing that knowledge, now you can directly draw the differential equation. So the differential equation for this particular block will be something like this. So M into d square x by dt square, because only X is given, only one block, that is why it is X only. M into d square x by dt square plus, then this is a spring constant, so it is K into X, basically K into X only. Then B, if you consider B is equal to dx by dt. Clear? So B, always the dash part or damper is proportional to first derivative of the displacement. Remember, here X is the displacement, whereas your mass element is, okay, here is proportional to, means the opposing force offered by this mass element is directly proportional to the second derivative of the displacement, that is d square x by dt square. Clear? Therefore, these are what the forces, opposing force actually. All these are the opposing force basically. This is the opposing force by this mass element. Kx is the opposing force by this spring element. B into dx by dt is the force again. This force again, it is the force offered by this, all these force. So three forces. How many actually? Spring is there, mass is there, your spring constant. Three forces. As three elements are there, or some opposing forces. Three types of opposing forces will act equivalently upon these three elements, and all these opposing forces equivalent to applied force F of t. So all these opposing forces equal to your F of t. This is your applied force. So these are the sum of opposing forces equal to applied force as per your according to Newton's second law. Clear? Now I think it is not required for me. I will erase this diagram now, because I already written the differential equation. For that only I need this diagram, otherwise no use. I think it's not required now. This is the differential equation. Remember that Now with this you can call it as equation number 1. This is the differential equation from this block diagram, physical system. Now this particular we have to convert into equivalent electrical. Okay, so here not required to apply the Laplace transformation. Normally we will do that. Basically, once the differential equation is written, normally we will think that to apply Laplace transformation. Remember that in this process, in this particular analogy, or we are transforming the mechanical into electrical. Now, in this particular transformation, not required to apply Laplace transformation. It is not required. So first of all, the first foremost thing is you must write the differential equations for the given block, or whatever the given block, maybe 1 or 2 or 3, for any number of blocks it may have the given problem. You write first the number of differential equations. Now for each differential equation you write the so the electrical equivalent equation we have to write. By using your force voltage analogy, by using force voltage analogy, the above expression can be, or the above equation you can say, the above equation can be represented as follows. Clear? Now I am applying the force voltage analogy to this. Means all these are mechanical elements. Now I am going to convert this into electrical equivalent. Now tell me, by using your force voltage analogy, recall that I already explained the particular parameter, how that corresponds to electrical. Your M corresponds to L. Clear? Your L corresponds to L. So M corresponds to L. Then d square x by dt square, how it becomes? So remember that it is very easy. So d square x by dt square you have to find out. For this, what we can write? It is d by dt of dx by dt. Like that you can write, no? Clear? So your d by dt is equal to dx by dt is further is dq by dt, your charge. dq by dt is equal to what? I know. That is why di by dt. Let us recall my previous this thing. So means d square x by dt square, you can write that di by dt. Therefore here I can say d square x by dt square can be written as di by dt. And one more important very important tip you need to mention, remember, is that it is a force voltage. Normally in voltage we use the Ohm's law, that is V is equal to IR. Clear? Force voltage, we are converting force into voltage. Again voltage means according to Ohm's law V is equal to IR, means V is equal to IR, means that whatever all these equation you must write the voltage equivalent values. This is the voltage equivalent values across each component will come actually. Say for example, this is inductor. Obviously this is a inductor. Inductor means you must immediately, without all this calculation, you easily can remember. Once you know that M is converted to L, then definitely in force voltage, as per the Ohm's law, what is the voltage of the L? If you take the inductor L, what is the voltage across L? If current I is there, VL is equal to L into di by dt. Obviously di by dt will come now here. That's it. Likewise you can write, not required to mention all these, or it is good to know, but you can write like this also. Therefore, clear? I think you understood, you all. So L into di by dt, this one. Next, K is nothing but your K is equal to what? 1 by C. 1 by capacitance. So 1 by capacitance. So capacitance, K is converted into capacitance. Then if you consider the capacitance C, this is the voltage. Say for example, Vc is the voltage, I is the current. Then what is Vc actually? Vc is equal to 1 by C integral of I dt, no? Obviously what it should come? Integral of I dt it will come. Directly you can write actually, because it is a voltage equivalent. Only if you do remember M equivalent to L, K equivalent to C, then what is the voltage across capacitor, that you must write, that's all. Okay, voltage, this is the voltage equivalent, voltage of inductor, this is the voltage of capacitor. Similarly, B, what is B? It is resistor. So for resistor, what you can write? Dx by dt R I, what is voltage? Voltage across resistor, V is equal to I into R. V is equal to I into R. Enough. This is equal to, and f of t is equal to your V of t, because force is converted into voltage. This is what force to voltage. Again, voltage is equal to all voltage equivalents. This is voltage equal to, this is also voltage, this is also voltage, this is also voltage. This is the voltage across resistor, voltage across capacitor, voltage across inductor. Clear? This is your equivalent equation. What is there in this? What difficulty is there? Clear? So this is what the electrical equivalent. If you clear, so now the next step is that by using this expression you draw the electrical network. That's all. You need to draw the electrical network. How it look like? Very simple. Very simple. Very simple. I will explain you here. So it is simply say, for example, in this particular expression, what we have, your input V of t is what? Voltage, no? Means the force is the input in mechanical. Correspondingly, what? So this is the input for electrical circuit. So we have to draw an electrical circuit with the input V of t. V of t is obviously input. And here, what is L actually? L is one, so it is L, it is C, R, means it is a RLC circuit basically. R, L, C. You can draw like this, and you can draw your V of t. This is I of t. This I of t, na? So I, this I is nothing but this I only. This I into dt, I into the same. This is R, L, C. This is electrical equivalent. That's all, using your force voltage analysis. So this particular expression can be represented in electrical circuit, equivalent circuit like this. This is the analogy. So that given simple mechanical translational can be shown with equivalent electrical circuit is like this. Understood? Okay, then we will finish off here, and I think you have enjoyed this, and we will continue. The next part of it means voltage, force current analogy, and remaining we will do some more examples on this for your better understanding in the subsequent presentations. Okay, we will stop at this. Okay, thank you one and all.